Hi friends, today my topic is application of mathematics in cryptography. Laws of nature and science. Kepler's law of planetary motion, Newton's law of motion, Darwin's law of natural selection, Kirchhoff's law, Moore's law. The number of transistors on Kirchhoff doubles about every 2 years. I thought it would be nice to have a law, so today for the first time I am unveiling my law. Galbraith's law. Every 10 years, someone invents some cryptography that at least 10 times slower than the previous ideas but has some new features. After another 10 years, it is fast enough to be practical and has a totally unexpected application. Both 1 and 2 are driven by mathematics. Encryption. Encryption allows two parties to communicate securely over an insecure channel. Traditional methods use a shared secret key between sender and receiver, called symmetric key cryptography. Cipher missions were fast and reliable and widely used. Public key cryptography. The sender only uses public information. The receiver has a secret key discovered in 1970s by James Ellis, Clifford Cox, Ron Weist, Len Handelman uses fairly elementary number theory. For example, the RSA crypto system works in the multiplicative group of integers modulo n, where n is equal to pq is a product of two large primes. Public key cryptography in 1970s. Computers were very slow then. I mean, if you think about a wax back in a day, trying to find a large prime numbers, it really took quite a long time, many minutes, maybe half an hour in some cases, depending on how big the prime was. And so the practical aspects of this were daunting at the time. Secured emails, secured phones were the kind of thing that struck as being the most likely areas of the first application. The wisdom of Ron Wist. But then it was an issue, and so we seen the evolution of computing power have its impact on public key cryptography, and I think this will continue. Well have will have these schemes now that seem complicated will become easier to implement as we get more tightly integrated computer systems. There's still lots of gains that can be made in implementing crypto in special purpose ways for some of these newer ideas that have come on the scene. Elliptic curve cryptography. Miller and Koblitz proposed elliptic curve crypto in mid 1980s. The idea was that it would be resist sub exponential index calculus algorithm and so be more efficient. At the time, RSA was okay, but subsequent progress in integer factoring made the advantages of ECC more relevant. Elliptical curves were viewed as much more advanced mathematics. Elliptic curve crypto. The security of crypto systems based on elliptic curve is not well understood, due in large part to the abstruse nature of elliptic curves. Few cryptographers understand elliptic curves. Over time, this may change, but for now, trying to get an evaluation of the security of an elliptic curve crypto systems is a bit like trying to get an evaluation of some recently discovered Chaldean poetry. Ron West, mid 1990s. Though the 1990s and 2000s elliptic curves become much more efficient due to new discoveries such as orthogamy curves and Edward curves, etc. Unanticipated advantages of elliptic curves include short public keys, important for public keys, certificates, and blockchain applications. Elliptic curves are now a very mature field and widely used. Pairing based cryptography, proposed around 2000 by Saki, Jovex, Bonon, Franklin. Much slower than traditional elliptic curve cryptography but promised new applications such as identity based cryptography and three party key exchange. More advanced mathematics, example greater use of algebraic geometry, pairing based cryptography, and Galbraith's law. fits my law that every 10 years sometime invents some cryptography that is at least 10 times slower than the previous ideas but has some new features based on new mathematics originally considered rather slow but nowadays considered very practical, not just due to Moore's law. Originally in 2000 thought to be useful for identity based crypto but actually used for blockchain, which wasn't a thing in 2000. Fully harmonic inscription FHE. Craig Gentry's PhD thesis in 2008 was a major breakthrough and solved a major open problem of harmonic inscription. Fully harmonic inscription is equal to computing on encrypted data. Key insight was bootstrapping, running the description algorithm harmonically to refresh ciphertext based on algebraic number theory lattices ridiculously slow. Summary: mid 1970s public key 1985 ECC, 1999 to 2001 pairings, 2008 FHE. Now isogenes and IO. Each new idea much slower than the previous tool, each using new mathematics, each having potential new applications. Conclusion: new systems are built on more advanced mathematics. New systems start slow and eventually become practical due to new ideas, not just Moore's law. The killer application is not the first application that is studied.